Hi, I'm Revati. I'm Assistant Professor, Department of Chemistry, Anna Hajra Women's College, Tirunelveli. Now, I'm going to explain the. My topic is coordination chemistry. So, in coordination chemistry, I'm first to focus on the BB theory. Okay. So, before enter the BB theory, we must know the transition, the nature of the transition metals. Why we need to study the nature of and the transition metal means in coordination compound the central metal ion, it is mostly the transition elements having the group the fourth periods. Okay, so what is why the descriptive study of transition metal means the transition metals, it is found in nature. Naturally we are getting the transition metals. Say for example, the rocks and minerals contain the transition metals. Okay, so the color of the compounds, it is mainly due to the presence of the transition metal ions. Say for example, the ruby. The color is red color. It is due to the presence of chromium. Okay, and also the biomolecules that are contained the transition metals that are involved in the functions of biomolecules. Say for example, the vitamin B2, the vitamin B12, it is the central metal ion is a cobalt. And also we are having them in hemoglobin, myoglobin, and the cytochromes. That is in the hemoglobin in the blood, that is in the human blood, having the central metal ion is iron. Okay, so the transition metal ions and their compound have the useful some of the applications. That is the steel and the stainless steel. It is made up of iron compound, so iron element, and also having some alloys. That is having in the lightweight alloys. It is made up of titanium. Okay, and also in various and the industries. Say for example, paint industry and dye industry, the transition metal compounds, it is used as a pigments. Okay, so the white color, it is the white color is the titanium oxide. Okay, so the transition metals, it is mostly used in the industrial purpose. So that's why we need to understand the applications of transition metals in the coordination compounds. Okay, so in the coordination compound, we will only focus on the fourth period transition elements. Okay, next. So in fourth period means, so fourth period means scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. So these are all the fourth period and the fourth period groups. Okay. Next one is what is the characteristics of and the transition metal means? The transition metals, it is having the multiple oxidation state. So that is the color of the compound, it is mainly due to the DD transitions. Okay, so the characteristics of transition, it is mainly due to the D electrons. Okay, so that is, and also it is exhibit the magnetic properties. Okay, so whether the coordination compound, it's a paramagnetic, diamagnetic, ferromagnetic, that can be that can be, it is understood by the that can be explained by the transition metals. Okay, so this transition metals, so and here we are the transition metals atomic number 21, 22, 20, titanium 22, 23 vanadium, 24 chromium, 25 manganese, 26 iron, 27 cobalt, 28 nickel, 29 copper, and 30 zinc. So this is the various oxidation state of and the transition elements. So this is the electronic the configuration of transition elements. In the outer orbitals, the scantium is 3d1 4s2, 3d2 4s2, 3D 3 4s2 and 4 3D 4 4s2 3D 5 4s2 3D 6 7 8. Okay, so these are all the electronic configurations of transition elements. Okay, so before entering the BB theory, we must know the basic concept of the coordination compounds. So the coordination compound, what is meant by coordination compounds? It's contain and one or more complexes. So the coordination compounds, it is always represent in the square bracket only. Okay, so the coordination, what is meant by coordination sphere means that is the metal and the ligands are bounded in it. That is, it's having the metal and the ligands. Okay, so what is meant by coordination number means number of donor atom. It is bonded to the central metal ions or atom in the complex. Okay, so how many number of donor atom it is get bonded? It is in this spaces we have to calculate the coordination number. So we are mostly commonly say the coordination number is 4 and 6. Okay, it is that is the coordination number. It is determined by the ligands. How many number of ligands which is get attached with the central metal atom. So here the ligands that is having the neutral charge of the coordination compounds. It is equal to the sum of the charges of metal ions and counter. So that is the charge in the metal ions and the chlorine compounds. That is the countervalency ions. Okay. Then what is meant by ligands means that is it is what are all the types of ligands means it is classified on the number of donor atom. So depending upon the number of donor atom the ligands may be calculated. So that is the types of ligands can be explained. The monodendrite ligand means having the one donor atom. Bidendrite ligand means two donor atom. Tetra means 4 donor atom. And hexa means 6 donor atom. That is the polydendrite ligands means the ligands having the 2 or more donor atoms. Okay, let us enter to the BB theory. So here the BB theory of transition elements in the coordination compounds. Okay, so what is the main focus on BB theory means it is explain the geometry and the magnetic behavior of many coordination compounds. So the coordination compounds geometry and magnetic behavior that can be it is explained or calculated by the on the basis of the BB theory. Okay, so in BB theory it is what are all the postulates of BB theory means here the central metal atom they provide the number of vacant orbitals. So here the central metal atoms having the vacant orbitals. Okay, the number of vacant orbitals and ligand. It is ligand must be contain the one lone pair of electrons. Okay, it is vacant orbitals. It is equal to its coordination number for the formation of covalent bond. Okay, so here we are having the metals and it is having this is the octahedral structure. In this octahedral structure and that is the bond which is existed between the metal and central metal atom, central metal and another ligand is it is a covalent bond. Okay, so that is it is called the coordinated. This is the covalent bond. Okay, next one is so the covalent bond it is formed by the suppose here the overlapping. Okay, the overlapping it is exists between the head-on overlapping means that is it is called the sigma bond. Sorry, it is a pi bonds. Okay, so pi bonds. Suppose the bond formation it is a sidewise overlapping means it is a sigma bond. So the overlapping is this is the sigma bond and this is the This is the pi bonds. Okay. So, and the pi bonds. Next one is here there are the various different type of hybridization that can be takes place in the metal orbitals. There are the various different types of hybridization that can be carried out in the metal orbitals. What is meant by hybridization means that is the mixing of orbitals. Okay, here this is the coordination number. Suppose if the metal having the coordination compound having the two coordination number means that is the structure is linear. The hybridization is sp hybridization. One s orbital, that is the overlapping which is exist between the s orbital and p orbitals. Suppose if you are having the coordination number 3 means it is the triconal planar sp2 hybridizations. Suppose if the coordination number is 4 means it is a tetrahedral complexes sp3 hybridization. 1 s orbitals and 3 p orbitals. That is the overlapping between the 1 s orbitals and 3 p orbitals. Suppose if you are the coordination number 5 means that is the triconal bipyramidal. Coordination number 6 means that is the octahedral complexes. So in VB theory we are only the focusing on the coordination number 4 and the coordination number 6. So the coordination number 4 and 6 means here we are having the tetrahedral complexes and also having the square planar structure. Okay. So that is the spin only magnetic moment value that can be calculated by using of this and can be calculated. Okay. So how to calculate the spin magnetic moment value? So that is the mu that will be equal to. So and the order certain mu that will be equal to, that is the spin magnetic moment, that is root of n into n plus 2. Okay, so that is the spin magnetic moment when that can be calculated by using this formula. What is meant by n means that is number of unpaired electrons. So number of unpaired electrons. So the spin magnetic moment value that can be calculated on the basis of number of unpaired electrons. That is the number of unpaired electrons. Okay. Suppose if you are having the number of unpaired electron 1 means the spin magnetic moment value that is 1.73. So that is the number of unpaired electrons 2 means 2.83. 3 means 3.87, 4, 4.90, 5, 5.92. So that is the spin magnetic moment can be calculated, that can be on the basis of VB theory. Okay. So what are all the applications of VB theory? Now we are going to see some of the examples. So before entering the examples, we must know that is the two different type of the ligands. One is strong field ligand, other one is weak field ligands. Okay. So what is meant by strong field ligands means that produce the large splitting. Okay, splitting of d orbitals, that is large splitting means that is the strong field ligand. So in strong field ligand, the spin that is it is low spin complexes, and the spin should be in pair. Spin that is spin is pair. Okay. So that is ligands that can produce a small splitting means it is a weak field ligands, that is the high spin complexes. Weak field ligands are high spin complex, that is spin free or unpaired. Okay, so that is the two type of ligands. Okay, here the spectrochemical series. Which one is the weak field ligands? Iron, bromine, chlorine, NO3, fluorine, These are all the weak field ligands. And water is the neutral ligands. Water, ammonia, this is the neutral. Sorry. Then this is the neutral, and NH is a strong field ligand is NH3NO2CO. This is the strong field ligand. So this is the spectrochemical series of weak field and strong field ligands. Okay. Now we are going to see some of the examples. This is the magnetic moment value and the geometry. It is explained on the basis of VB theory. Okay. So here the one of the example CO H2O 6 2 plus. So this is the central metal ion is cobalt and the ligand is water molecule. How much of ligands? That is the 6 ligands. Okay, this is the 6 coordination compounds, that is the octahedral complexes. Okay, so this is octahedral complex. So first we are going to find out the oxidation state of cobalt atom. Okay, so what is the nature? How to calculate the oxidation state of cobalt atom? We didn't know the oxidation state of cobalt, so it is taken as X. Okay, so we are here the water having this is the neutral ligands. Okay, so minus 6 into 0. Okay, that will be equal to plus 2. So X is equal to plus 2. That is the cobalt having the plus 2 oxidation state. Okay. So what is the atomic number of cobalt atom? So here when they already known scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. So 21, 22, 23, 24, 25, 26, 27, 28 and 29 and 30. Okay, so what is the atomic number of cobalt atom? 27. So 27 means that is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7. So this is the electronic configuration of cobalt atom. Okay. So this cobalt atom having the plus 2 oxidation state. Okay. So plus 2 oxidation state means how many number of electrons that can be divided? That is 2 electrons that can be lost. So the electronic configuration of cobalt is cobalt 2 plus ion is, so 1s and the organ, 3d7, 4s 0, 3d7, 4s 0. This is the electronic configurations. Okay, so now fill the d orbitals. So 1, 2, 3, 4 and 4s, 4p and 4d. 1, 2, 3, 4. So 3d, 4s, 4p and 4d. So 3d7 means, so this is the neutral ligands. So 1, 2, 3, 4, 5, 6, 7. Okay, 6, 7. Okay, so that is in the, here we are having the number of unpaired electron is 3. So number of unpaired electron, this is the that is a weak field ligands, and this is the next water is a weak field ligand, and it is a high spin complexes, and that is the spin free. that is spin-free complexes. Okay, so here we are having a number of unpaired electron is 3. So number of unpaired electron is 3 means that is the magnetic moment value is 3.87. Okay, here we are having the how many number of that is ligand, 6 ligands. So 6 ligands which is occupied in the vacant orbital of the central metal atoms, that is 1, 2, 3, 4, 5, 6, 7. Sorry, 6. So 6. So that is in the water molecule in H2O, H2O, in H2O, H2O and H2O. So 6 in a vacant orbital that can be occupied by the water molecules. Okay. So this is the outer orbital complexes. Okay. So this is the outer orbital complexes. So their hybridization is sp3d2 hybridization. So this is the octahedral complexes. sp3d2 means 1, 3 plus 2. So 5 plus 1, 6. So this is the sp3d2 hybridization. Here we are having the number of unpaired electrons. Okay, so this is having the paramagnetic complex. Okay, so number of unpaired electrons which is present in means this is the paramagnetic complexes. Another one example for that is the octahedral complex CN6 3 minus. Okay, CN6. The same procedure is followed as before. See the example. Here we are having the strong field ligand. So the ligand is strong field ligands. Okay, strong field ligand. First we are going to see the oxidation state where X. So Cn minus oxidation state minus 1 into 6 that is equal to minus 3. So X minus 6 that is equal to minus 3. X is equal to plus 6 minus 3. So X is equal to plus 3. So the oxidation state of cobalt atom is plus 3 oxidation state. So the electronic configuration is 3d6 4s0. That is losing of 3 electrons. 3d6 4s2. So that is the electronic, how to they define the electronic configuration means. So 1, 2, 3, 4, 5, 6. So this is the strong field ligands that is having the low spin complexes, and then the spin will be pair. Spin pairing. Spin pair. Okay. So spin pair means that is set aside diamagnetic complexes. So diamagnetic complex is 4s. So 3d, 4s, 4p and 4d. 1, 2, 3, 4. 4d. Okay. So here we are having the 6 ligands. That is the 6 ligand. It is occupied in the vacant orbital 4, 5 and 6. So this is the sp3d2 hybridization. sp3d2 hybridizations. Okay. So this is the outer orbital complexes. Okay. Next, another one example of, sorry, it is a, this is a inner, that is previous example is inner orbital complexes. So So that is CO CN 6 3 minus, that is it is inner orbital complexes. Inner orbital complexes, there is no there is having unpaired, no unpaired electrons. So it is the spin magnetic moment value is 0. The spin magnetic moment value is 0. So the sp3 d2 hybridization, this is the octahedral complexes. Octahedral complexes. Okay, next we can see that another one example of in coordination number 4. So that is the nickel. Nickel having the coordination number, that is the atomic number is 28. So scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. So 21, 22, 23, 24, 25, 26, 27, 28, 29 and 30. So this is a coordination number is 7, that is atomic number is 28. Okay, so 28. First we have to find out the oxidation number of nickel, where X is equal to 0. X is, that is, it is taken as X. That is the nickel having the oxidation number is, that is 0. Okay, so here in the cobalt atom is, that is the strong field ligands. So strong field ligands means how to fill this? So 3D, what is the electronic configuration? 1s2, 2s2, that is argon, 3D, 8, 4s2. So 4s, sorry. So here the nickel compound, it is having the coordination number 4. It is a square planar complex having the hybridization is sp3 hybridization. It is a tetrahedral complexes, and that is platinum Cl4 2 minus. This is the hybridization is dsp2 hybridization. It is a square planar complexes. Okay, so having the coordination number 4, that are the two type of hybridization is sp3 hybridization is a tetrahedral and dsp2 hybridization is a square planar complexes. Thank you.